Hi, thank you. I'm excited to be here today, and thank you everyone for coming out. Last year I came to PyData tutorials day, and I really enjoyed it. So I hope you enjoy your day here at PyData and your entire conference. So today I'm going to be talking about computer vision with PyTorch. And I'm going to start off by talking about what computer vision is. Generally speaking, computer vision is the process of extracting patterns from images. And in recent years, convolutional neural networks have gotten much better at performance on computer vision tasks has increased dramatically in recent years with the rise of convolutional neural networks. I'm going to talk about PyTorch. PyTorch is a popular framework for implementing neural networks. It runs on GPU. It's a popular choice for working with images, text, and audio data. Afterwards, I'm going to go through a few examples of common tasks in computer vision, including classification, object detection, and segmentation. Notebooks are available on GitHub. So we'll cover this more when we get to that point in the presentation. But there's a GitHub link. They're both Jupyter notebooks. And if you don't have Condor or PyTorch installed, there are Google Colab links to run code in the browser. Afterwards, there will be a Q&A session. I anticipate we'll have a lot of time for questions, so feel free to ask away. So what is computer vision? Computer vision is an interdisciplinary field focused on the development of using algorithms to interpret digital images and videos. So here I have a few common computer vision tasks. So given an image, what's in it? Is it a dog? Is it a cat? Is it a person? That's classification. Object detection focuses on producing bounding boxes of objects, like in this case it's a horse. You could do cars, you could do people, that sort of thing. And segmentation produces a pixel-wise mask for objects in an image. These are just a few computer vision tasks. In general, anything you can train a neural network to do, you can do with computer vision. The key idea is that convolutional neural networks have gotten a lot better in recent years. So feature extraction in computer vision has gotten a lot better. So here on the right, I show the top 5 error rate on the ImageNet Large-Scale Visual Recognition Challenge. This is a competition where a large data set with over 1 million images, where the goal is to predict the class of a given image. So it might be an airplane, or it might be a fire hydrant, that sort of thing. And before 2012, traditional machine learning methods were used on ImageNet. It wasn't until 2012 that convolutional neural networks were first used. And that led to a dramatic drop in the top 5 error rate. Currently, the last ImageNet contest was held in 2017, but the benchmark is still maintained, just not in contest form. And as of 2019, the top 5 error rate is down at 1.8%. So computer vision has come a long way in the last 6 or 7 years. And this is due to a number of factors. First, improved algorithms. So convolutional neural network architectures have gotten better. New architectures are constantly being released on the order of every few months. That's coupled with improved hardware. So computer vision is computationally intensive. And the algorithms have existed for a while, but the hardware has been improving rapidly with NVIDIA GPUs that run CUDA and Google TPUs that run algorithms efficiently. Along with hardware comes software support for that hardware. The two biggest software platforms in computer vision are TensorFlow, which was released by Google in 2015, and PyTorch, which was released by Facebook in 2016. And both platforms are being actively developed. And these platforms essentially are NumPy with support for GPUs and also support for neural network operations and image data. So I've been talking about convolutional neural networks. I'm going to talk at a high level how they work. So this is an early architecture. So the input is some image. In this case, it's a 32 by 32 character. And so this image, of course, is represented as a matrix or a tensor so that computers can work with it. Convolutions are applied to the input image. So, in a case like this, you might map a 5 by 5 pixel region in the initial image to a 1 by 1 region in what's called a feature map. And each convolution has different weights. And the idea there is that you can extract different features from an input image. So each of these feature maps might find, at a high level, might find something like vertical lines, horizontal lines, corners, which is great. And then there's a subsampling or pooling step where the dimensionality of these feature maps are reduced. So you might do something like look at a 2 by 2 grid in a feature map and find the max value or find the minimum value or something like that. And you can repeat this process a few times and as you progress deeper into the network, you get features over larger and larger regions of the image. And finally, you might represent the image as a one-dimensional tensor. And then using traditional methods, depending on what your target variable is, you can have a standard fully connected network. This is covered in more detail elsewhere. I have references in the slides. I'd say the main idea is that convolutional neural networks are really good at extracting features from images, and what you do with those features depends on what you want to do with the image. So I know here I said some of the common tasks are classification, detecting objects, segmentation, but you can do things like predicting distance to object, you can do style transfer, you can do a lot of things. But the common component in modern computer vision systems is that convolutional neural networks are used to extract features. Another thing that's been really great, especially recently with PyTorch and TensorFlow, is pre-trained models. So training models from scratch is computationally intensive. The ImageNet data set is over 1 million images. Most of these models have millions of weights. It's expensive. It can be challenging to get right the first time. So pre-trained models are really helpful. So for classification, for example, there are a bunch of pre-trained models on ImageNet. For object detection, models are typically pre-trained on COCO, which is a data set that has 80 different classes. And PyTorch comes standard with a number of pre-trained models. We'll go through this in the notebook section, but it's really easy to call a pre-trained model from PyTorch to detect objects or to classify an image. And any model that's available in the research, you can find on GitHub somewhere, or you can download from PyTorch Hub. So even if a model is not in the standard PyTorch distribution, you can download it from somewhere. And in computer vision, because one property is that this process here of extracting features is fairly general. You might be doing things like looking for vertical lines in an image or looking for corners. And the feature extraction process tends to transfer well between tasks. So it's common in computer vision to start with a pre-trained model either for initial weights, or you can even freeze the weights and then add additional classes to a model. So a model is trained to detect dogs. You could train it to detect cats if you have a data set of cat images, that sort of thing. Okay. And so I've been talking about PyTorch. This talk is about PyTorch. I'm going to go into a little bit more detail about what PyTorch is. PyTorch is a library for tensor operations. It was released by Facebook in 2016. The style of PyTorch is fast experimentation. It is a Python first library. It's dynamically typed, like Python, which is nice. It's essentially NumPy with GPU support. There's a lot of integrations with NumPy. So you define tensors. You can put tensors on GPUs. And there's a lot of built-in support for like data loaders to load your data set, training neural networks. And there's a Torch Vision package which helps with transforms for images. And OK, so I'm going to switch over to more hands-on on GitHub. So here, so I'm going to go through a few notebooks on the tutorial GitHub page. If you want to follow along on your laptop, feel free. You can either run the notebooks locally if you have Conda and PyTorch installed. It takes a little while to install because there's a bunch of CUDA libraries. I was trying to get the latest version on my laptop last night, and it took a while. Also, each notebook has a Colab link. So if you go to this GitHub page, and you click on a notebook, and you click on this link, the notebook will actually open in the browser. I just discovered Colab a few days ago, but it's a service by Google where you can run notebooks in the cloud with GPU support for free. Couple of sign-in screens the first time, but it's not too bad. And this is really useful because Google actually has PyTorch pre-installed. So the notebook should run smoothly in Colab. OK. And again, like this is listed as a beginner level tutorial. So I'm going to start by going over the very basics. And then I'll provide references to more intensive, like object detection training methods and stuff if you're interested later. OK. So this is the Getting Started notebook. So if you haven't already, if you don't already have PyTorch installed, you can install it with conda install PyTorch-c PyTorch. It's recommended to use conda over pip for installing PyTorch. You'll get 1.3, the most recent version. Pip will probably give you 1.0. PyTorch does come with CUDA libraries, so this does take a while. Also install Torch Vision. You can install that with pip. That's easy. And like as I just showed you, especially if you're looking to experiment, Google Colab is a good option for getting these notebooks running, for running code cells. Also, if you go to the PyTorch, so the PyTorch webpage has a lot of good materials from research to production. If you click on the tutorials page and you click on tutorial, like these tutorials you can run in Google Colab. Okay. So I guess let's clear output. OK, so I'm going to run this from scratch. So typically, you start by importing Torch and Torch Vision. Especially Torch Vision has a bunch of different libraries, so you might import torchvision.transforms as transforms or something. There are a number of conventions around that. So Torch tensors are essentially NumPy arrays. So here I have a tensor of zeros, and I can do something like x plus 1. And now I have a tensor of ones. And if I say x plus torch tensor of like torch.1's 3 or something like this. Oh, okay. Times 2, get a tensor of 2's. So if you use NumPy, Torch is designed to use a lot of the same APIs as NumPy. There are a couple differences that we'll get to later. And just another example, you can define you can create a Torch tensor from a list, that sort of thing. Okay, and Torch tensors can be converted to and from NumPy arrays. So here I have a NumPy array, 321, and there's a method from NumPy. So I can convert this NumPy array into a Torch tensor. One thing to note is that there is a data type, so this is an int32. Data types matter when you're running on GPUs. GPUs are highly parallelized, and every bit that's allocated to a number or an integer in a tensor matters. So just be aware of the data type. And sometimes you'll get an error like, oh, you gave a float, but you were supposed to give an integer 16. If you care about data type, most of the time you can type dtype. And then maybe I can say something like float. Doing this from memory, it's probably not right. Maybe it's float 32. Oh, no, I think it's, okay, I think it's a string. Oh, from NumPy takes no arguments, okay. Well, if you do torch.tensor, I know takes a float. You can pass in a data type as a float or something like that. From NumPy, now I remember, actually uses the same data type that's assigned to NumPy. So if you have a NumPy array, you can specify a data type as an integer or a float, and that will be copied into the PyTorch tensor. And again, so here, if you want to go from a Torch tensor to a NumPy array, you can call NumPy, and you just get a NumPy array. Okay. So Torch is very similar to NumPy for basic operations. One of the things that is really useful for computer vision is support for CUDA. So a very common design pattern in Torch scripts is to, let me make this a little bit bigger. Okay. Is to have this torch.CUDA is available. So a lot of times you have a script. If someone has a GPU, you want it to run on GPU. If someone doesn't have a GPU, you want the script to still run. So this is a really nice design pattern. So you say, if CUDA is available, use the CUDA device or the GPU. And otherwise, set the device to CPU. I'm going to back up a little bit and talk about devices. So in NumPy, it's assumed that all your data lives on the CPU. So there's no concept of device. In Torch, there's this concept of device where you either have data that lives on the CPU or data that lives on the GPU. And for things to work properly, you either want all the data and the computation to be done on CPU or entirely on GPU. Here, okay, I provide an example of creating a tensor and setting the device to CPU. If this laptop had a GPU enabled, I think Colab has GPU enabled. It'll find the CUDA device and here instead of CPU, it'll say GPU 0.
Do we need to, on Colab, do we need to do something to enable the GPU? Because mine says CPU.
I haven't tested that. I know that there is a way to get GPU on Colab. You can get up to 12 hours for free. But I don't want to try and figure it out during the presentation. But I know there's a way to do it. Okay, for working with images, the Python image library is very helpful. If you're on Colab, just to note, Colab is for, if you're on Colab, you need to download the image from the internet, so use this like wget command to grab the image. If you clone the repo, you don't need to do this. So Python image library supports loading images easily. So here you can see like I open a JPEG image of a dog and a bicycle, and I show the image. And the Torch Vision package can easily convert this into a tensor. So here I'm using a Torch Vision transform to tensor. And I get an image that's 3 for the RGB channels and 576 by 768, which is the dimensions of the image. I'll note that in torchvision.transforms, there's another number of other operations if you want to do pre-processing, where maybe you flip the image by 180 degrees, or you rotate the image, or you do image augmentation. You can compose transforms together, more complicated ones, and use that for image augmentation. So there is one gotcha. This is probably the biggest gotcha that I've run into in Torch. And that's if you're working with, if you're feeding data into models, there's a convention that you add an extra dimension at the beginning, and that's for the batch size. And that's because it's like typically it's more efficient to pass in a big matrix as opposed to a bunch of small matrices. So you might have a batch size in a typical case of 16 or 32, depending on GPU memory. So even if you're passing in a single image, convention here is to add an extra dimension for the batch size. So there's this unsqueeze operator that'll add a dimension. And if you want to get rid of the dimension, you can do image tensor dot squeeze and shape, and that will get rid of the dimension. So this is just something to pay attention to. Okay. And so at this point, we have an image. It's loaded into CPU. If you're using a GPU device, you can use a design pattern like this. So for inference with pre-trained models, I'm going to use the Colab version. Okay. So pre-trained computer vision models are useful, particularly if you have a common task. So if you want to do something like detect a person in an image, tell whether an image is a dog or a cat, or maybe like segment an object in an image, common tasks. There's a good chance that there's a pre-trained model off the shelf that you can use for that task. If you have a more custom data set, like for example, if you care about maybe identifying your dog as opposed to dogs in general, you'll likely need to train a specific model for that task, which we'll cover next. Okay, so, okay. So running this in Colab. So we're going to start with imports. So this will download the image from GitHub. And going to display the image. Okay, so we have this image tensor. So insert code cell. So just examining the image tensor a little bit. Bunch of RGB values. And okay, so Cocoa is a popular data set. Oh, did this last night too. Computer vision isn't as popular as Disney, although it should be. OK. So Coco is a data set that consists of common objects in context. So there's 80 of these. So for example, you want to look at dogs. Let's see. OK, this is a nice explorer. So you can see, OK, we have a dog, we have a frisbee. OK, this image has a dog and a frisbee. This image has a dog and a hairdryer. This image has a dog looking out the window. OK, a dog and a horse. Coco has a lot of variety, and it's free to use. It's open source. So for object detection, Coco is the data set that's most commonly used. And so you can see classes include person, bicycle, car, motorcycle. And now, so here I'm using mask-RCNN, which is a model that's pre-trained or it's a model architecture that's good for object detection, that's good for segmentation. And running this in PyTorch is just a few lines of code. So there's torchvision.models. Let's see. So torchvision.models comes with a bunch of pre-trained models. So there's some for classification, detection. I like mask-RCNN a lot. Segmentation. Oh. And then there's a few models for semantic segmentation as well. Again, these are just models that PyTorch has included in the main library as a convenience. I find them to be helpful. Of course, anything that's in the literature you can find on Git, like the researchers will post on GitHub. And also, you're welcome to build your own architectures as well. So here, there's a pre-trained equals true flag if you want to include pre-trained model weights. This eval function, I haven't discussed gradients in PyTorch in depth. But one difference between PyTorch and NumPy is that PyTorch actually tracks gradients of tensors in a graph. And I don't want to go into too much detail until we get to the training section. But eval basically says don't record the gradient, like don't update the gradient, don't worry about gradients. Just use this for evaluation as opposed to training. Okay. So this is the key line. So we import the model, we run prediction. This 0 is like so remember how I said there's a batch size? The 0 means grab the first element. So we're only passing in one image. So it's a batch size of 1. So the 0 says grab the first element in the batch. One thing to just be aware of is that there is a batch size. Pay attention to that. Here I add names. Like the default return type is a tensor. Here I return names so we can interpret what's in the image. So here the result of running mask-RCNN on this image is we have a bunch of bounding boxes. If I recall correctly, this is xmin, xmax, ymin, ymax. Every object detection framework has different conventions on the 4 numbers that specify the box. So the labels 1822, if we look at the names of those, dog, bicycle, 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 car, truck, potted plant. And here, if you look at the scores, these are numbers 0 to 1 that specify how confident the network is in a prediction. So you can see that for dog, it's very confidence score of 99, 98 for bicycle, and then it falls off a bit after that. 80 for bicycle, 75, 75, and then 50 for truck. And then below that, it's 33 or below. So in practice, a lot of times you set a threshold and say, let's look at predictions with a confidence score above 50% or something. Those confidence scores depend on task and depend on your training set and test set. So I definitely recommend choosing a threshold like after examining the results. And so I looked at these predictions last night, and it predicts this dog with high confidence. It predicts this bike with high confidence. It gets a little bit confused by this motorcycle in the corner. It has two different predictions there. So it gets a little bit confused by this. And then for this truck, was it a car or is it a truck? It thinks it's both. It's a little bit confused there too. But, you know, which is pretty typical performance. For the things that humans can see easily, like this is obviously a dog, this is a bike, this is probably a motorcycle, it's a little bit obscured. This is somewhere between a car and a truck. So I'd say sort of object detection methods are only as good as, like if there's any human ambiguity in labeling, like maybe some labelers would label this motorcycle, maybe some wouldn't. If there's ambiguity in human labels, there might be ambiguity in predictions as well. Okay. Let's see, how am I doing on time? Okay. I want to leave plenty of time for questions. So this is the last notebook. This is some references on training computer vision models in PyTorch. This is significantly more involved than essentially the 2 lines of using a pre-trained model. And as I said before, the key feature of computer vision is this model architecture. So for extracting features, you're going to use convolutional neural networks. A lot of times it makes sense to use, like for applications, it makes sense to use existing model architectures, perhaps with pre-trained model weights as a starting point. A lot of research has gone into those, and they tend to perform better than defining something from scratch for complex problems. So a common approach is to use model weights pre-trained on ImageNet and defining the rest of the network and training the rest of the network or fine-tuning the weights. So typical formulas defining a Torch dataset and data loader. So in Torch, you define an object called, you typically define an object called the dataset. Define data loaders that dynamically load data from the dataset. Typically, this is a tensor X representing an image and Y being whatever label you're trying to predict. Determine, define model architecture. Again, here it's useful to borrow from existing architectures, initialize model weights. Loss function will depend on what target you're looking at. So for something like classification, you can use the standard cross entropy for classification. For something like object detection, let's see. So for object detection or segmentation, the loss function isn't as clear. I can tell you for RCNN, the loss function looks something like, is there an object in this box? Is that object what the class label predicts? And how good are the bounding, and how good is the bounding box prediction? Although if you're doing something like object detection, you can use the standard loss function for object detection. Select an optimizer. Same with any neural network optimization. I like to use Atom. You need a data set. So if you're training, you can either provide your own data set. Like if you wanted to build a model that said, like, is there a car in this parking spot? You might provide a number of images with a car in the parking spot, a number of images without a car, and train a model on that. There are also a lot of open source data sets available with images and labels available. And And I think it's important to benchmark the performance of the model. A lot of times you're going to be doing hyperparameter tuning. You're going to be trying maybe different architectures. Maybe you want to know when to stop training. So it's important to look at your loss function, maybe look at accuracy, and determine how long you want to train for. PyTorch has a number of tutorials on model training. So there's one on training a simple classifier. This is a simple 2-layer model from scratch. I think I'll go over this briefly. There's a object detection fine-tuning tutorial. This one I found very useful in practice. It is a bit more involved. You need to download a data set from the internet. You need to download PyCoco tools and stuff. So this I like because it gets into a lot of the nitty-gritty of how do you pre-process images, and how do you get them into a usable form. And for neural transfer, I include this as an example of cool things that you can do with computer vision. So here, the idea is that you have a style image and a content image, and you have a loss function that incorporates matching the content of the content image and the style of the style image, and you can get something cool like this. So feel free to check that out. I think, and these are all available as Colab notebooks, so feel free to go through them. I'm going to go through the training classifier tutorial. So I'm going to open this in, I think, and I'm just going to stick it a high level on the website for now. So if you're working with images, again, Pillow, the Python image library, is very useful for loading images. opencv, Open Computer Vision, is also very useful in Python. That's like if you want to do simple operations like change the contrast of an image or flip an image, you can do simple operations like that with opencv. Again, like PyTorch also supports audio and text with libraries out of the box. So this is the CFAR10 dataset. It has different classes like airplane, bird, cat, deer, frog. It's small, so it's fast to train. CFAR10 was more popular sort of in these days in 2010, 2012, when ImageNet was quite hard. CFAR10 was easier because there's only 10 classes instead of 1,000. So CFAR10 is good for fast training, and it was a very popular benchmark several years ago. Okay, so again, train, test, split, define a network, define a loss function, train the network, and then benchmark the network on test data. So again, import Torch Vision transforms. Okay, so now when I was talking about, let me zoom in a little bit. Okay, so this is an example of pre-processing. So torch.transforms allows you to perform a series of transforms on some sort of image, because typically you have, maybe some folder. The folder has a bunch of JPEG images. What you want is you want tensors. You want to be able to operate on these on GPU. And, like sometimes you need to normalize if you're doing image augmentation. Sometimes you want to flip. Maybe you want to rotate. Maybe you want to randomly crop to get a more robust training set. So transforms.compose lets you group multiple transforms together. So here, first we take the object, convert it to a torch tensor, and then we use a normalize function to standardize the image. So the torch documentation is quite good. Okay, so let's see, okay. I'm trying to get a list of torch transforms, but just like as an example, you can do a random affine transformation, you can do a random apply, that sort of thing. So really useful for pre-processing. Some of these data sets are predefined in Torch. So if you want to download a bunch of these CFAR10 images, all you need to do is define a dataset CFAR10. Oh, sorry. Oh, okay, download equals true. So this will actually download the dataset for you. And it'll preprocess the images according to this transform. The data loader is, this is a very useful idea too. So this is actually a dynamic data loader. So you might have some data set that's a bunch of images on disk, or in this case, a bunch of images on PyTorch servers. And this data loader will actually dynamically grab images from the train set as they're needed. So if you say, okay, I have this data set and I have this data loader, nothing happens. And then when you want to grab, when you want to perform training and you want to grab, say, like in this case, 4 images at a time as the batch size, it'll grab 4 images from the data set like at runtime and give those to you. So that's a bit different than TensorFlow, which is statically typed. And so I think one of the biggest, and PyTorch and TensorFlow are both great libraries, very well supported. I think one of the factors that pushes people one way or the other is, do you want something like TensorFlow that's statically typed, which is maybe, well, Python's dynamically typed. So if you're using Python, I think dynamic typing is consistent with a lot of Python-like things. If you're working in something like Java, well, PyTorch isn't in Java, but Java is statically typed, and so having a statically typed library and statically typed tensor library makes sense. Okay, and same thing for test set. Okay, you can show images using matplotlib, again, integrated tightly with NumPy. Okay, and so that's defining the data set. Again, you can use some of these standard data sets. There's support for that. So this is defining a neural network. So Torch has a neural network library, torch.nn, and a functional library of functions that you can apply within neural networks. So here, when you define a network, you define a new class. So this is called net, but you could call this like anything you want. You could call this like, like my network or anything you want. It extends the neural network.module. A module is either a network or a subnetwork. You can have networks feed into networks. And you need a constructor method. And the constructor method calls the constructor of neuralnet.module. Typically in the constructor, you define your layers. So here there's a convolutional layer, a pooling layer, a convolutional layer, and 3 fully connected layers. So this is a simple network. Looks a lot like this one, convolution pool, fully connected layers. In practice, for modern architectures like ResNet, these get a lot deeper. You might have something like 50 layers, a bunch of convolutions and poolings. Non-linearities like batch norm and ReLU are very helpful. If you're dealing with a network that's that deep, a lot of times it makes sense to grab a ResNet definition or something like that, and then maybe tweak it if you need to. But for a shallow network like this, you can do it both ways. You can either load a definition that's essentially a file that looks like this, or you can write it yourself. And then you define forward. And so this is when you pass an input X into the network, what happens. So in this case, you have an input X, you apply a convolution, and then you apply ReLU. Okay, and then you apply a pooling function. So here, you apply the second convolution with the weights specified here. You apply ReLU, and then you pool. View is kind of a funny thing. It lets you change the shape of tensors. So here, -1 means fill this dimension as needed. So this basically says change the shape. I believe that this flattens the tensor into, let's see. I believe in this case that this is flattening the tensor into one long, like an x by 1 tensor. And then here there's a fully connected and ReLU, fully connected and ReLU, and a fully connected layer at the end. So as I said before, Torch is dynamically typed. Like if you're using TensorFlow, you'd compile the model, and then you'd run it, and you can't change it. In PyTorch, if you want to, you can actually go in and change some of these. Like you could run a pass with this network, and then you could actually go in and add like a +2 in here. And the next time the network runs, it would actually like add 2. So dynamic typing lets you do interesting things like that. It lets you get in a little bit of trouble, but not too much trouble. So loss function optimizer, cross entropy loss is pretty standard for classification. Choice of optimizer matters, so experiment with different learning rates. Typically, so the learning rate specifies how rapidly the parameters are updated. Learning rate on the order of 0.001 is pretty standard. If your network explodes, we reduce your learning rate. And this is what training looks like. This is pretty boilerplate code. So you run training for a certain number of epochs. You actually need to keep track of loss and stuff yourself. So boilerplate code looks something like this. So you go through data in your train loader. You get your inputs, typically images and labels from the data set. This is important, actually. This is kind of a gotcha. So torch tensors have gradients associated with them. So when you're in training mode and you evaluate the network, gradients are being saved. And this can do some weird things. So I would recommend sticking with this sort of boilerplate code and using, okay, let's see. Okay, there's no eval here, but I think we went over before there's this eval mode. And so if you're, at test time, you want to use evaluation mode, so you're not actually training your model at test time. So loss is this criterion, cross entropy loss. Backwards is interesting. So this says update the model weights based on the loss function that you observed during training. And optimizer.step. Okay. And I think that I need to recall the difference between loss.backwards and optimizer.step. But together, they update the weights in the model. And then you can keep track of the running loss and print the running loss over time so that you can evaluate how well your network is doing. You can serialize your model to disk, often as a .pytorch file. And then if you evaluate the model on test data, you can say, okay, like you can look at the predicted outputs. Okay, so this is just a 1-hour presentation. I hope that I've covered some of the most important points. I wanted to point to some some of the best resources that I found personally. So PyTorch.org, I've been in and out of there throughout this presentation. And that has really great documentation and tutorials. Also, anything that comes out of research is pretty quickly reflected in the PyTorch, like in the PyTorch documentation. Stanford has a really good course on CNNs and visual recognition. It's free, it's online, there are lecture notes, syllabus, really useful. They go in depth into the linear algebra of everything. So that's, if you're looking for sort of like a 1 semester long explanation, I'd recommend that. And if you're interested in the details of deep learning, I'd recommend the Deep Learning book by Ian Goodfellow. There's a couple of chapters on computer vision as well. So that's it for my presentation. Thank you for listening. And if there are any questions, I'd be happy to take them. Yes.
So I realize this is a bit of a moot point if you're using pre-built models and adjusting them. But if I'm actually trying to build a model from scratch and I'm setting the hyperparameters for what I'm doing, what heuristics do you have on what kind of are good things to do for my hyperparameter tuning?
Yeah, very good question. So the question is hyperparameter tuning. I'd say for that, definitely a deep learning book by Ian Goodfellow. Like if you want a really long answer, it's very long, very accurate, very to the point. So I'm going to start with, I'm going to give 2 answers. So the first answer is kind of specific to computer vision. And it's that, like, if you have a picture of a dog, for example, that's like 1,000 pixels or something. It's really the features in a dog are really complicated. So if you want good performance in practice on image data, you want to start by extracting features with a CNN. And then you get maybe some like a feature vector, and then you go off that. So I mean, you maybe say, okay, a image that has corners and vertical lines in these places is a dog. So now, so typically with computer vision, you want to start at that. You want to start hyperparameter tuning at that point. I'd say there's a number of approaches. Probably in practice for computer vision, you want to try different architectures. So here, like for classification, there's a bunch of backbones. So I'd try a bunch of different backbones, benchmark the performance, see which backbone works best. You can also go into the backbones and add layers or remove layers. Most of the time, if you make a model deeper, you'll improve the performance. Let's see what else. Also, image augmentation for computer vision is important. So, if you have an image of a dog, maybe you flip it horizontally, maybe you crop it. And in general, image augmentations help avoid overfitting and generally improve performance. So those would be some of the first things that I look at. Generally speaking, training computer vision models is expensive. So if you're training, a small model on like a small tensor, you might have the luxury of trying a million different like hyperparameter settings. For computer vision, the data sets are typically large. So I think in practice, people tend to stick with a few core angles of like adding layers, image augmentation, different backbones. Is probably like if you want to get good performance in practice, those are some of the most promising directions.
I
Yes.
believe intelligent
That's a really good question. So I don't know on CPU threads. I do know on GPU. So on GPU, okay. So here it says CPU. So here, so on GPU, this is running on CUDA 0, which means like the first GPU. If you have multiple GPUs, you can say you can set the device to CUDA:1, and that'll be the second GPU, and so on and so forth. That's for managing GPUs, which is typically where the bottleneck is for image processing. I don't actually know how Torch handles CPU threading, but Torch is Python first, so I think if you wanted to run on multiple threads, you could look into multiprocessing. I probably shouldn't Google that. Not super I haven't worked with multiple threads. My experience, at least, is that like at least when I run into cost, like there's a cost of actually running the model. So if you have a big model, you have a lot of cost in the model. And also, if you have data on CPU, like a typical GPU is like 8 gigs of memory. So a lot of times you have bottlenecks between moving data from CPU to GPU, and that's like another potential bottleneck. But very good question. Yes?
In the second notebook, when we saw the results of the image detection, there are multiple labels that are listed multiple times, like 3 bicycles and things like that. Does that represent multiple bicycles in the same image or multiple shapes that this bicycle can be?
Right. So here, good question. So I probably should have plotted the bounding boxes. Both. The short answer is both. So you can see that this first bicycle is from pixel 160 to 170 across. So that corresponds to this big bicycle here. And then there's 2 more bicycle predictions here. So those are 3 and 4. And you can see that these are overlapping. So these are in the 472 to 679 region. So I believe that's this region here. So I think that there's 2 different predictions for a bicycle in this region. And depending on the methods, like RCNN has different tricks in the loss function to try and prevent duplicate predictions of the same image. But that different models handle duplicate prediction differently. Yes?
So my question is more around, once you've run the model and everything, you talked about the benchmark performance.
Yeah.
But actually, what will be some of the steps, or what is your advice or best practices, to be able to set that benchmark?
Right. That's a very good question. And I think that really depends on the task. So there's 2 types of benchmarks, really. One is the loss function, or the accuracy or whatever metric like the model spits out. So like let's say you're trying to predict, like you have a classification problem and you're trying to predict whether an image is a dog. So one metric might be accuracy, and say like, okay, like this model is 80% accurate. And so kind of like the naive approach there is to try different. If the metric you care about most is accuracy, the naive approach is to try a bunch of different models, print out the accuracy of each model, and select the model with the highest accuracy. That's kind of like level 0. Accuracy is a metric that has real-world meaning. There are other metrics like cross-entropy that I was talking about that doesn't, might get in trouble for saying this, but it doesn't have much intuitive meaning. You know, if you say the cross entropy of a model is this, it doesn't mean much in practice, but it is really nice to optimize over. So for classification, you could use mean squared error, but people have switched over to cross entropy because it's really nice for optimization. But I think it's really helpful to think about what you're using the model for. Like if you're using the model to predict, you know, whether there's a car in a parking spot, like think about your use case. Like, you know, like how much do you care about false positives, false negatives? Like what problem are you trying to solve? And maybe you say, okay, I want to get a text message if there's a car here and it's okay to have a false positive but not a false negative, that sort of thing. So I think the best benchmarks are tied into the like use case that the model is being used for.
Okay, because when you went through the PyTorch, right, into the tutorial itself, I have an output, right, and it's telling me this is the different loss functions, and it will
Yep.
give me an output of like 10, 20.
Yes.
So which one of those I will be using or share it with my stakeholders?
Yes. So let's go here. So for this case, so this is the training loss. So this is the cross entropy loss. So lower is better. So this is a good check. The model's getting better. This doesn't really mean much. Like you never, like people don't report, you know, like this is more for internal use, not for presentations, not for that sort of thing. If the loss is going down, training is working. When the loss function stabilized, that's a good time to stop training. Let's see. So here, in terms of external facing loss, like these would be the metrics that you might look at. So I apologize, I skipped over this quickly in the original presentation. So here you might say, okay, with torch.nograd, this is similar to eval in that it stops the computation of gradients. You go through the test images that you haven't seen during training. You run the net on a series of test images. Like in this case, like, you know, you get a bunch of output predictions. You take the largest, you make a prediction with that label, and then here's where you're computing the loss function. You're saying, okay, does the most likely prediction match the label? So here for this particular model, you might report something like a 55% accuracy on the test set, and you might break it down by image. So this particular classifier does really well with ships, but doesn't do well with cats. Does that answer your question?
Yes, and the reason why I'm asking is because I have very engaged stakeholders, and even though you don't want to show them, you know, training, they still ask, you know, I want to see this result. I want to see, you know, I'm paying you to build something. What does that mean?
Don't show the training.
They want to see the training. So for them, it's like dream field. So it's basically, you know, you're giving them like a one-on-one intro to data science.
I would say, you know, like I have this model. This model was trained on this data set. Like here's the performance of this model on the test set. The training metrics are useful for debugging during training. But I think ultimately what matters is generalization, and that's on the test set. So test set metrics are ultimately what matters, and training set metrics are just what gets you there.
Great, thank you.
Yes?
Does PyTorch have something that you can map back, like class activation mapping, so it shows a heat map on what it detected as a certain object?
Yes, really good question. Okay. So, let's see, get started. So there's this thing called TensorBoard. It's made by Google. So fortunately, Facebook and Google are kind of, like, I guess, like they both work on deep learning research. So TensorBoard is this TensorFlow tool for visualizing models. And you can also use it in PyTorch. So you might get something like this. Is this? Okay, I can't run it. But one common workflow is to write your training data in a certain log format, and then you can load that data into TensorBoard. And TensorBoard has really good support for visualizations. Let's see, I'm trying to come up with an example. Training loss. I know there's an activation plot. Oh. Okay. Let's see. Okay. So you might get something that looks like this, where you can look at visualize weights and activations in your network. Does that answer your question? Okay. Any other questions?
Thanks, Daniel Brooks, for leading us through your talk on computer vision with PyTorch. Everyone, please give him another round of applause.